Okay, so this is the second of 3 recordings that are just review material for you to go through. And in this review, we're looking at what I'm deeming here reactions of biological importance, essentially a review of some of the organic chemistry that we might encounter in this class. And as we consider metabolism, one of the ways to approach this subject is to think about the chemical details, in particular the chemical strategies that a cell will employ to carry out a particular metabolic path, or metabolic paths, plural. And that can be a very rewarding study. Now, I will be honest with you, we're not going to do that in this class. I am going to approach metabolism more from a physiological and health standpoint, simply because the majority of you are going to go into fields where that will be more important to you, and therefore it can be also more interesting to you. That doesn't mean that a detailed analysis at an organic chemistry level of metabolic pathways isn't important. It is important, but I'm not going to do it. However, having said that, we are going to encounter some of these concepts in this class. We are going to go through some mechanism, and so I would like you to be on the same page as I am as we go through metabolic pathways. You cannot avoid metabolic pathways in a class of metabolism, so we're certainly not going to do that. And because we're going to do that, we will also talk about some of the strategies as we move forward. Now, going through these slides, there are 2 major principles that I want to introduce. The first one you're looking at right now, and then we'll get to nucleophiles and electrophiles here in a little bit, and we'll then kind of go off of those 2 major principles. The first one here is looking at cleavage of bonds. And really, you can think about it also as condensation, or the making of bonds. And when you think about, for instance, catabolism, you have bond cleavage that has to occur. You have to break apart carbon-carbon bonds. We're going to talk about glucose becoming 6 carbon dioxide molecules. So glucose is comprised of 6 carbons, all of which are covalently bound to each other. And then we're going to see those become carbon dioxide, so we're going to break all those carbon-carbon bonds. That's bond cleavage. You have also, at the same time, you can go through the formation of bonds, carbon-carbon bonds. For instance, the making of glucose would require carbon-carbon bonds to be formed. And so that would then be kind of the reverse of what we're talking about in terms of cleavage, but very similar chemistry, just in reverse. And so when we think about then cleavage of carbon-carbon bonds or carbon-hydrogen bonds, let's just look at carbon-carbon bonds. It can happen either through what's called homolytic cleavage or through heterolytic cleavage. Let's just go down here. Homolytic cleavage at the top, get my pen here. Homolytic cleavage is when the electrons in this covalent bond here are split equally between the 2 atoms, and you get what we consider carbon radicals. Heterolytic cleavage, on the other hand, is when these electrons, let me get my blue pen back, and these electrons are split unequally, and one of the carbons gets both electrons, the other one doesn't, and then you get a carb anion and a carbocation. Now, in this class, this type of cleavage is going to be more prevalent than the other type. That's not to say that the homolytic cleavage is not important in metabolism. It is. In particular, in nucleotide biosynthesis, we would, if we were to go through that, we would see lots of what's called free radical chemistry. And we'd have to think about that kind of cleavage and that kind of condensation reactions. But we're not going to go through that. We don't have the time to do that. So we're going to see primarily this. Now, the interesting thing about this, carbocations and carbanions, okay, these are actually intermediates that are very unstable. In fact, in some cases, they're so unstable that to form them is nearly impossible, if not impossible, in biological scenarios, even with enzymes acting as catalysts. So one of the strategies that we would find commonly employed in a metabolic pathway is to introduce something into that molecule to stabilize the formation of carbocations and carbanions. And one of the most common means of doing that is to introduce a carbonyl group. this carbonyl group, right? You see this carbon here is electrophilic, and this oxygen is fairly nucleophilic. That oxygen has great electron drawing power. And if you were to put that carbonyl group next to the formation of, let's say, a carbanion, shown here, then you can get rearrangements that you see in those red arrows, where these electrons come here and these electrons come here. And that then forms this intermediate, where you have a fairly stable negatively charged oxygen. You have a fairly stable double bond between these two carbons. And that can happen simply by introducing this carbonyl group. So that's one of the strategies that you'll find in metabolic pathways, is that they will have some means of introducing a carbonyl next to a carbon that needs to be cleaved or needs to be used to make a bond, and undergo a condensation reaction. You can do the same thing. We get a different colored pin here. Do the same thing by introducing an imine group. This is not as common, but it is something that can happen as well. Now, in addition, the carbonyl group, so coming back up to this, what you see here in blue, come down here, that carbonyl group has a much greater capacity to carry out this type of chemistry and form this intermediate if there's some sort of metal ion adjacent to it, or if there's something that can donate a proton, an acid. Metal ions would be cofactors found in enzyme active sites, magnesium being really common, manganese being another one that's pretty common, nickel is fairly common in that as well, or some acid. So serine, for instance, has a hydroxyl group that can be fairly acidic in enzyme active sites and can donate a proton that can then stabilize this, making it a hydroxyl group. Okay, so it really depends on the scenario, but this is fairly common. Right? And all that can happen by the introduction of then this carbonyl or this imine. Okay? And that will then stabilize, like, let's say, a carbanion. Now, let's go on and look at this, and you see here, for instance, okay, we have this carbonyl here, we have this carbonyl here, we have this carbonyl here. In all three scenarios, what that carbonyl is doing is it is going to stabilize a carbanion intermediate. This, and you don't really see it here because they don't write out all the chemistry, but in a decarboxylation reaction, that carbon would have to go through a carbanion intermediate. And so you have this aldo condensation or a Claisen ester condensation or decarboxylation of beta-keto acid. All of those are really common reactions in biology, and when you see them, generally speaking, they have to have either an imine or this carbonyl adjacent to the carbon that's going through that type of chemistry. Now, I don't really care that you know the big difference between an aldo condensation, a Claisen ester condensation reaction, nor a decarboxylation reaction even. That's more like organic chemistry, and certainly I'm sure you're familiar with these types of reactions, but that carbonyl makes it very important. Now, let's go one step further, and this brings up one more point. Still thinking here about that major concept of bond cleavage, carbanions, carbocations, and let's look at two different reactions here. One of them directly related to what we're talking about here, and those are isomerization reactions. So what you see here, this is an isomerization reaction. Isomerization reactions are catalyzed by isomerases. And what we see here is glucose 6-phosphate, which is this isomer of the 6-carbon carbohydrate, being converted to fructose 6-phosphate, which is another isomer of a 6-carbon carbohydrate. And what you'll notice here is that we've moved the carbonyl one carbon over. It's on the first carbon here in glucose, it's on the second carbon here in fructose. And what that does is it allows for that carbonyl to be moved next to this carbon here, carbon 3. And that carbon here is actually going to have to go through a carbanion intermediate because this molecule is going to be split in the glycolytic pathway. So this enzyme here is actually enzyme number 2, and glycolysis. Enzyme number 4, an enzyme called aldolase, catalyzes an aldo condensation reaction, actually in reverse. But aldolase, it is going to then split fructose. It's actually going to be 1,6-bisphosphate by the time we get there, but it's going to split it right here, and you have to have that carbonyl at that carbon to do that reaction. So this isomerization reaction is just a perfect example of how the introduction of a carbonyl sets up the aldolase reaction. Okay, 2 steps later. Now, certainly isomerizations, while we're still on this, certainly isomerization reactions do more than just move, a carbonyl group. And what we see here, what we have here is a cis double bond, and this isomerase is going to make that a trans double bond. Again, we could go through the mechanism. I'm not going to do that, but we're just going from cis to trans. And this is really important in this beta oxidation pathway, which is essentially lipid catabolism pathway, because the enzyme that works on this intermediate only can work on a trans double bond. Okay, so you have to go from a cis to a trans, right? And that's another isomerization reaction. Now, elimination reactions can introduce double bonds, and that's what we see here. And that's a really important step also in beta oxidation, or the synthesis of fatty acids, where we take, essentially this is a dehydration reaction, okay, and that then makes this double bond. There are actually a family of enzymes called dehydrotases that will do this, okay, that then make these double bonds in beta oxidation that then are very important to carry out the rest of the oxidation of the lipid. Okay, you can go in the reverse direction as well. Add water through a hydration reaction. Add the water to the double bond and get rid of it. Okay, so that's a very important type of reaction as well that you would see. Right. Now, this brings us to our next major topic. Right, the first one being bond cleavage. The next major topic would be nucleophiles and electrophiles. And I've already mentioned nucleophiles and electrophiles, actually, but let me go ahead and mention them again and actually define them. On page 511, you will find these verbatim. So I'm plagiarizing, I guess, but I'm using quotations and I'm telling you about it, so I guess I'm not plagiarizing. But these are the definitions that your book gives. So these are textbook definition of nucleophile, and that's a nucleophile is a functional groups rich in and capable of donating electrons. Electrophiles are electron-deficient functional groups that seek electrons. Again, you've been through organic chemistry, you know what these are. So common nucleophiles, here, carbanion is one, okay, an uncharged amine group, imidazole and hydroxide. Just to say something here, histidine, right? The enzyme, or not the enzyme, the amino acid side chain histidine ends with a imidazole group. Histidine is really common to be found in enzyme active sites because of its role. Because of lots of things. It can act as an acid base, but it can also play a role in what are called nucleophilic substitution reactions. Okay, so those are really important nucleophiles. Electrophiles, you see on the other side, we've already mentioned this. The carbon of a carbonyl is a really important electrophile. What you don't see here, and I guess I should use a different color. Let me use a different color. So green will be electrophiles. What you don't see here is carbocations. Okay, these are electrophiles as well. Okay. The two most important or common that you're going to see is this carbon of the carbonyl and this phosphate of a phosphate group or inorganic phosphate group. Okay, this happens to be the breakdown product of HCP, a very important reaction. Okay, now this brings us to one of the other strategies, right, and a very common type of reaction that you will see in biochemistry in this nucleophilic substitutions, also called or also known as group transfer reactions. That's actually the term that your book uses, but nucleophilic substitution works as well. And what you see here, I mean, the chemistry is fairly straightforward. Again, I don't want to spend a lot of time on this, but here's a nucleophile, all right, that's attacking an electrophile, and you get this type of rearrangement. Oftentimes these will go through a tetrahedral intermediate. Not terribly important, but the main point here is this, that in this type of chemistry, when you see this rearrangement, X is the leaving group. Now, it turns out that not all organic functional groups are equal in terms of their ability to act as a leaving group. So one of the strategies that you will see in terms of metabolic pathways is to introduce leaving groups, or what are considered good leaving groups. Let me give you an example here. Okay, so don't worry about the fact that this says glucose. Just don't worry about it. Okay, don't worry about the fact that it says glucose 6-phosphate. Doesn't matter. Okay, but hydroxyls are really poor leaving groups. They're not good at it. However, this inorganic phosphate, also just goes by PI, is a really good leaving group. Okay, and you can get, through a nucleophilic substitution reaction, you can get this hydroxyl to essentially, through, again, nucleophilic substitution, to be a phosphate group. So you go through this, right? Hydroxyl group attacks the phosphate. Okay, and then they're not writing all the chemistry here, but that phosphate is transferred. In this case, HCP is the donor. Okay, ADP is the breakdown product, and we have this then phosphate now attached to whatever R is. That phosphate is a great leaving group, and then we can go through another nucleophilic substitution where the phosphate leaves and we put something else there. Right? So, very important type of reaction. ATP, this highlights some of the reason that ATP is so important as a molecule, because it is used as a phosphate donor. That phosphate becomes a good leaving group for something else. Okay, there's lots of other reasons why ATP is important, but this is certainly one of them. Okay. Now, when you look at this reaction, these are oftentimes catalyzed by enzymes called kinases. Okay, and you will, I'm sure, well, not will, but you have, I'm sure, run into kinases, and you will certainly run into more. You're going to run into a lot of kinases in this class. Kinases just essentially carry out phosphoryl group transfers, okay, where this phosphate group is called the phosphoryl group, okay? All right. So another important strategy in chemistry, okay, and biochemistry. Now, last set of reactions. I won't spend a ton of time on this, but we have to talk about redox reactions. You cannot understate the importance of redox reactions to biology. What you were looking at here, this is just, again, in the way of reminder. You've gone through Gen Chem 1 and 2. You certainly know what, by this time, a redox reaction is. This is a great or very common example of redox reaction, where you have iron 2 plus copper 2 to then carry out this redox reaction to make iron 3 and copper 1 plus. And what we see here then is the transfer of electrons. Remember, redox reactions are just movement of electrons from one molecule to another. And the iron in this case is losing electrons, so this would be the half reactions. Remember, you write out half reactions. And this half reaction actually represents the oxidation of iron. And so we'd say that iron is oxidized, meaning that it lost its electrons, and we'd say that then iron is the reducing agent. Okay. On the other hand, we have the other half reaction, the reduction half reaction of copper. Copper is reduced, and we say that it then gains electrons, and we call it the oxidizing agent. Strictly review there, I know, but you have to keep those things in mind. Okay, so this is our other half reaction. Okay. Now, that's fairly straightforward. When you look at this, it's fairly straightforward to see what is gaining, what is losing electrons, because you have a change in charge, right? And electrons carry negative charge, so you can fairly easily figure out, okay, what is being oxidized, what is being reduced in this. But what about carbons, right? So how do we know the redox state of a carbon? Well, this is based off of what is bound to that carbon. So you start here at methane, and we've got methane here bound to 4 different hydrogens. And we're going to assign a value of 8 in terms of its redox state to that carbon, because that carbon is more electrophilic than I did say electrophilic, but what I meant to say is it has a greater electron drawing power, and in that term is escaping my mind. Oh, electronegativity. There it is. Electrophilic. Electronegativity. We say that the carbon is more electronegative than the hydrogen. And because of that, we can say that it owns each of the electrons, or shares them unequally with the hydrogen, and we say it owns them, okay, with the bonds to hydrogen. As you move down this list, right, you will find out that carbon is forming bonds to other atoms of greater electronegativity. For instance, in this ethane, carbon, this carbon in red, is forming 3 bonds to hydrogen, and it still owns all of those electrons, 6 electrons total, but it forms it forms a covalent bond with another carbon. And we then say it owns one of those 2 electrons because it has equal electronegativity to that carbon. So we say that the redox state of that carbon is 7. Right? As we start to introduce oxygen, for instance, here in ethanol, oxygen is more electronegative to carbon. Then, so if oxygen is bound to carbon, then we'd say that carbon is going to have a more oxidized state. Okay, so as you start to think about this and you start to move down this, and I'll let you study this on your own, but anytime we add bonds that are to a carbon that are either to another carbon, so a double bond, introduction of a double bond, for instance, or to an oxygen or to a nitrogen, we're saying that carbon is oxidized. Anytime we are taking a carbon and we're taking it, from a double bond to, let's say, a single bond, then we're reducing that. Or if we're removing oxygen, we're reducing it. If we're removing nitrogen, we're reducing it. Or if we're adding hydrogen, we're reducing that carbon. So keep those things in mind as we move through this. Now, that brings up then something called dehydrogenation. Dehydrogenation is a type of redox reaction that we're going to see in biochemistry, very common. And this is a biochemical reaction in which 2 electrons and 2 protons are transferred from one molecule to another. Right? So 2 electrons and 2 protons are transferred from one molecule to another in a dehydrogenation reaction. And that's our key here. 2 electrons, 2 protons. Okay. Now these are always catalyzed by a class of enzyme called dehydrogenases. Dehydrogenases carry out dehydrogenation reactions. What you were looking at here at the bottom, this is an example of a dehydrogenation reaction that we will actually encounter in the upcoming lectures in this class. And that is lactate is going to become pyruvate. So this carbon here, that carbon, if you look at the redox state, it has an electron here, it has an electron here, it has 2 electrons of that hydrogen there, so we'd say that owns 4 electrons. Whoops. This carbon here now has a double bond to oxygen and only owns electron here and electron here, so we say it owns 2 electrons. So 2 electrons have been removed in this reaction, going from lactate to pyruvate. At the same time, 2 hydrogens, this one and this one, are going to come out as well. Okay? And this is a very, very common thing in biochemistry. And oftentimes you will see this, it can go in either direction, by the way. We looked at it this way, but it can also go in this direction. But we'll see this going from alcohols to ketones or aldehydes, or ketones, aldehydes to alcohols. Okay, that would be a very common thing to do. It can also go from single bonds to double bonds. Dehydrogenation reactions will do that as well. Okay, so that's dehydrogenation. Now, something needs to accept these electrons, and coenzymes are really common acceptors or electron acceptors, or if you're going in the reverse, electron donors in these dehydrogenation reaction. And the 2 most common are NAD and NADH, NAD plus and NADH, that's a reduced and oxidized form, and another one called FAD and FADH2. I will show you NAD plus here and NADH, and then as we progress through the class, you'll eventually see FAD and FADH2. But just to give you an example here of this. Now, what you're looking at, this is essentially NAD plus. NAD plus represents the oxidized form of this coenzyme, and the plus comes from this charge right here on that base. Now, NAD, what does that stand for? NAD stands for nicotinamide adenine dinucleotide. Now, dinucleotide means there's 2 nucleotides, and if I were to get a different colored pen here, and I were to put a line right here, then that separates the 2 nucleotides in this molecule. A nucleotide is something that has a phosphate moiety, a ribose ring, and a base. Below the red line is the adenine nucleotide. Above that is the nicotinamide nucleotide. And really the business end, for our purposes here in our discussion, is this ring right here, which is the base of the nicotinamide nucleotide. And that base, when it's in this positive form, is oxidized. It can accept 2 electrons. Now they're showing the 2 electrons here, but in reality, those two electrons, let me go ahead and put an X here, and I'm going to go ahead and put an X through this. Those two electrons come on a hydride anion, like this. Okay, and then there's going to be another proton. I'll go ahead and just make it some other color. Well, maybe I won't make it some other color. My pen's not working. But anyway, there's going to be another proton. It's going to be added to this. And of course, dehydrogenation reaction, two protons are moved, two electrons are moved. The two electrons in this case are going to be moved as a hydride anion. And then the other proton is going to come. And in fact, this proton is just going to become this. Okay, it's just going to go off and be buffered out of solution. The hydride anion, though, is going to be attached to this carbon. Now, they talk about A side and B side here. Don't worry about that too much. Okay, see this or here, A side or B side. But it's really this carbon here is oxidized, and then when it accepts that hydride anion, it becomes what we call NADH, the reduced form of this. All right. So this is one example of a coenzyme that can be an electron acceptor of these electrons in dehydrogenation reactions. FAD is another common one as well, and we'll encounter that as we go through this course. Now, the last thing that we need to discuss in regards to redox reactions is the free energy change that would be found in these redox reactions. And this introduces another fairly fundamental free energy equation that can be used to calculate the free energy change of a redox reaction. Now, to do that, you have to have what's called the reduction potential of the two molecules involved, the electron acceptor and the electron donor. And by having the reduction potential, that will allow you to calculate this delta E. Now, the delta N, I'm sorry, not the delta N, but the N is essentially the number of electrons. Okay, F is Faraday's constant, 96.5 kilojoules per mole per volt. You can look that up in any textbook or any website, really. But delta E is our change in reduction potential. Now, what is a reduction potential? The reduction potential is a measure of an atom's affinity or a molecule's affinity for electrons, meaning the ability for that atom or molecule to take electrons in a redox reaction. And not all atoms or molecules are equal in their capacity to remove electrons from other atoms or molecules, and we measure that ability using the reduction potential. Now, let's go to our next slide then. Our next slide shows a table. It's a table very similar to what you would find in Chapter 13, although the one in Chapter 13 is more expanded. But here we see then half reactions, and these are reduction half reactions and the reduction potential for each of those half reactions. Starting all the way up here at oxygen, and going all the way down here to this molecule called alpha-ketoglutarate. Now, this is a really high reduction potential. This represents a really low reduction potential. Notice it goes from positive numbers to negative numbers. And this represents, this one at the top here represents a really strong oxidizing agent. And the reason being that this has a high affinity for electrons. Oxygen happens to be one of the strongest oxidizing agents. It can suck electrons right off of this. Oops. Right? Where did it go? Oh, I'm going the wrong way. There we go. Right? So that's a strong oxidizing agent. Obviously, this would be weak. Weak affinity for electrons, weak oxidizing agent. Now, understand then what we're saying here is that there are some molecules that have a greater capacity to take electrons from other molecules. Well, if that is the case then, and that is the scenario then those molecules that have this greater capacity to take electrons are spontaneously going to take electrons from those that have a weaker affinity for it. Now, we can measure that based off of calculating what's called the delta E, or the change in reduction potential, where we take the reduction potential of the electron acceptor minus the reduction potential of the electron donor. Notice that the electron donor is oxidized, electron acceptor is reduced. And so let's go ahead and just do an example of this, okay? And we'll look here at this reduction potential, which happens to be the reduction potential of NAD plus NADH. Right? And we'll look here at the reduction potential of, that's 0.045, of a molecule called ubiquinone, which we will encounter when we talk about oxidative phosphorylation electron transport chain. And let's just say for some reason the biological scenario requires that the electron acceptor be the NAD plus molecule. It's going to accept electrons, and it's going to accept electrons from this ubiquinol, which is our electron donor. Well, if that's the case, then our delta E is going to have a negative value. And if we put a negative value up here, then that negative times this negative here will make a positive delta G, and we would say that this is an inorganic process. Now, hopefully that makes sense based off of what I've said to you, because what we're saying here is that our electron acceptor has a weaker affinity for electrons than our electron donor. So we're having something with a weaker affinity for electrons take electrons from something with a stronger affinity. That spontaneously won't occur. Now, if we were to switch this scenario, we were to do this, where ubiquinone becomes the electron acceptor and NADH becomes electron donor, then we have a reduction potential or change in reduction potential of the same magnitude but opposite sign. Do that up here, now we have a positive here times that negative, that makes for a negative delta G. And this would be an exergonic process. The basis of the electron transport chain, which we'll talk about later on in the semester, is this type of reaction where it's favorable. The basis of photosynthesis, which we won't talk about in this class, but is essentially based off of this type of reaction, where energy from the sun has to drive that in the direction of its products. Now, that is it for our discussion on reactions, and in particular redox reactions, because that's how we're finishing out. If you have any questions, by all means, please contact me.